Continuing on with the solutions for the end of your review, number 2, which is all about functions. This next section deals with sequences. When you first determine what type it is, get the common difference or common ratio, that's the DNR part, write the recursive and explicit function, and then get a sub 11, which means get the 11th term of the sequence. We'll use the explicit function to do that. Alright, so when you figure out what type this is, well, first you need to figure out what pattern this is. -2 to 6, -18, 54. This would be a pattern of timesing by -3. The sign changes, means you're timesing by a negative each time. And -2 times 6 is, -2 times -3 is positive 6 times -3 times -3. You get that. So this type is going to be geometric, which is the timesing by something every time. And the common ratio, this one is a common ratio because it's geometric. And if you ever want to figure out what that is, you just take any term and divide by the previous one, and it'll give it to you. And it's also the number you multiply by every time. The recursive functions, you always should write down where you start your sequence. So this one, a sub 1, is going to be -2 because that's where the whole sequence starts. And then you need to say what the pattern is. Well, every number is equal to the previous one. This is a sub n and a sub n minus 1, say. Well, you're going to take your previous number and you're going to times by -3. Ta-da! That's a recursive function. That's all you need to put down. On the explicit ones, you're going to start with a sub n. And then you need to put down your a sub 1, which in this case is -2, and that goes in front of your common ratio to the n minus 1 power. And that's just the formula that we used. It's going to have an exponent of n minus 1. Your common ratio goes there at the bottom. A sub 1 goes out front. You can also write this so you can go back one term and do a sub 0 in front, which would be 2/3, because you do 2 divided by the -3, and then you'll have -3 to the n power. Those are equivalent there. Either one works, but this is the one we did in class. I know some of the other classes did this form here. Anyway, moving on to a sub 11. On a sub 11, you need to get the 11th term of the sequence, which means you're going to take 11 and you're going to plug it in right there. So we do -2 times -3 to the 11 minus 1 power. You'll get -2 times -3 to the 10th power, and this is where calculators come in handy. And so you're going to put in -3 to the hold on a second, to the 10th power, and then you're going to times that by -2 times by 2 negative, and that's going to give you a fairly large number of -118,098. Yeah, if you play on a calculator, make sure you use parentheses around the 3, and then to do the exponent, you do the caret 10 part, and I'll do the exponent for you. So there we go, there's our first one. 18, this one has a different pattern. Starts at -19, -24, -29. This is just a pattern of subtracting 5 every time, which makes this guy arithmetic. Or arithmetic. Arithmetic's the adjective form. And arithmetic ones have a common difference, and the common difference is what you're adding every time. So if you're subtracting 5 every time, your common difference is going to be -5. The recursive ones are always going to be a similar form. You write down what the first number of the sequence is, and then you're going to write down what happens with each preceding number. Every term is equal to the previous one, and then this one, the pattern subtract 5. So you subtract 5 on the end. The explicit function for arithmetic ones is a little bit different. You're going to put your common difference in front of n minus 1. And then you're going to add your initial value, which was -19. You can simplify this one down if you times that through. You'll get -5n plus 5, and then subtract 19, which will give you negative 5n minus 14. And this is a lot like the equation of a line because arithmetic and linear functions are very, very, very similar. So there we go. This top one's okay, but the simplified one is better just because it's simplified. And now if you want to get a sub 11, I'm going to use this one to make it a little bit easier on myself. Negative 5 times 11. You just take the 11 and put it in for n, and then subtract 14. Negative 5 times 11 is negative 55. If you subtract 14, basically adding those negative numbers together, which will give you negative 69, and that's the answer for this one. Moving on to the last two. Write an explicit function to describe the situation. You inherited land, purchased for $30,000 back in 1960. The value of the land is increased approximately 5% each year. Okay, this percent increase tells me it's going to be a geometric sequence, which happens to be the same thing as an exponential function. And this 30,000 is going to be my initial value, so I'm going to use that explicit function for geometric ones. The initial value goes out front, 30,000. And then this 5% each year, that is a 5% increase, which translates to timesing by 105% each year, which is, if you write as a decimal, 1.05. And so that's what's going to go right here, 1.05. And then my exponent, I'm going to have it be just n minus 1. So, yeah, okay, I'm going to say it's n minus 1. And, because that's the formula we've been using, you can just write it as n, but the difference is what you say in the next part. We can leave it like this. Whether you put n or n minus 1 doesn't really matter as long as you know what number to plug in when you have to evaluate it somewhere, which is what's happening on number 20. You need to determine the land now, which is 2015. 2015 is 45 years after the initial purchase. And so if we used just n here, we would just plug in 45 because each year there are 45 years since the start. But if we said this was n minus 1, then the first year purchase would mean 0. The 0th year, the year it was purchased would be year 1, and so 45 years later would be the 46th term of the sequence, so you plug in 46. But we didn't do n minus 1, we just did n, and so you can just plug in 45 into your explicit function here. Either way, you'll get 45 for the exponent, and if you do 1.05 to the 45th power, and then you times by the 30,000, you'll get a whole lot of stuff. You'll get $269,550.23, which is a lot of money, which is kind of what you expect with a 5% increase each year for 45 years, which is a really long time. And there's our solutions.